Good morning, Srini. How are you?
I'm fine, teacher.
Today you want 1 hour or 2 hour?
One.
Okay. Anything you want to ask? Any question you want to ask?
Hello?
Any question you want to ask?
No, teacher.
So we leave it for next week. The question
The Wednesday.
we
Yeah.
should finish by next week. And since you say the quiz has helped you, after we have
I
completed,
do revision and then
you do revision, I give you the quiz, and then we will do the
to see
past
how
paper.
prepared I am.
We do the past paper. Get you ready?
Yeah, you're right, and like do exercise, then you won't be scared like that.
That's why I say after I teach you, you just review through. That save a lot of time. Then you go over the exercise. Because without doing exercise, you cannot force it in.
Just like keep doing only.
It's like physics. Sorry, it's like math. Right? It's like math. You cannot study math one. Only review through and try to refresh your memory, that's all. So that is what physics is all about. It's a lot of math involved. So if you don't keep on reinforcing it, you forget it, then you will have less confidence.
Yes, teacher.
That's why I also like you when I was your age. Frightened of teacher, they're not us. And then don't you at least you trust your revision book. For me, I trust my teacher only and the teacher's notes. That's why I didn't do that well. Okay, let us go to energy. Yeah. We have gone to cell induction, so we give you time to do your homework. Energy is a short topic. Energy stored in inductor, page 213 to 215. Okay, that is your power supply or voltage. Your cell has your current flowing. There's your inductor or inductance L. Energy is stored in magnetic field. That's the main thing to remember. Because when you pass your current, the current start to rise, there's a change in magnetic field. So the energy is stored in the magnetic field. So V, as we say, is the voltage applied across the inductor, and the cell inductance is L, and we drive a current through I. And we know that as a current flow, there's an induced EMF. So it means that this voltage there must be greater or equal to the back EMF. Remember, the back EMF is always opposing this current. Right? That's what this formula is telling us. Right? Negative sign. That back EMF oppose this rise in current. There's a change in current with time. So that voltage must be greater than your back EMF across the inductor. Okay, so it means that, sorry, if we have put that equals to minus that, then we have to put a positive sign here. And it should be a positive sign here. Okay, we have said that the supply voltage, that is the supply voltage, or voltage supply, must be equal to the back EMF, negative or back EMF, because the two are in different direction. That's why it's going to be a positive sign here. Okay, can see my mistake there. And to be careless, there should be a positive sign here. Right? Power supply by the battery is just a that voltage there times that current, P equals to VI. So remember the power supply, right? Power is the rate of work done, or rate of energy supply, right? U is the energy, du dt equals to L di, and there's an I here. Okay, I'm just replacing this power with du dt, and then there's your V, L di dt, and then there's your V where we replace, and there's your I. Okay, so the dt and dt can cancel off. Okay, so I got du L di times I, right? So I can integrate that from 0. We start from 0 current to a final current I, Li di dt, that one. So integrate that to be half Li squared. Right? So in inductor, energy is stored in the magnetic field, right? Depending on the current and cell inductance. Same as capacitor. Capacitor is C. Right? Instead of L is C, it's still half. And then instead of I is V squared. Right? That one is stored, if it's a capacitor, it's stored in the electric field. Okay, try this question. An inductor or cell inductance 40 millihenry carry a constant current 20 ampere. What is the energy stored in the inductor? Right? Just getting you to use the formula. Got the answer?
Divided 40 times
Half
10 to the
L,
power
half
93.
Li squared. Half Li squared. Remember to change it to SI unit. Right? Energy stored is half Li squared. Put in your value and calculate out.
You mean 1/2 mv square,
Half Li squared. Right? L is 40. You have to change it to SI unit. And then current is 20. If the energy is completely discharged in 5 milliseconds, calculate the mean power. Okay, we are just using what we have learned. What is the mean power? Yeah, mean power is energy divided by time. That's all.
So 8.0 divided 5.
Remember to change to SI unit. Okay, 5 millisecond becomes 0.005. So I get 1.6 millivolt. That's your mean power. Mean back EMF induced in the inductor. What formula to use? Basically getting you to use all the formula that we have learned as well. Any idea what formula we should use? Yeah. The cell inductance formula lor. Back EMF equals to, don't worry about negative sign, L di dt, because you won't worry about Lenz's law. It tells us the direction only. And put in your value lor. Right? Your L 40 becomes 0.04 Henry. And then your I Initial is 20, change it to 0. So there's a change in, and there's your time. Right? 5 milliseconds becomes 0.005. I get 160 volts. Can. That's why it's important to do homework. Then you can remember the formula. Okay, you can see very short, completed already. All this formula you need to know how to use for this topic. So that is under cell induction. And right, that's the formula. And then the last formula that we have learned. Okay, then we will come to mutual inductance. Same as cell inductance, right? Instead of L, we change to M there, that's all. Instead of L, we change to M there. Instead of N, we have N for primary and N for secondary, that's all. This is for primary, one coil only. The one got 2 coils. So we go to cell mutual induction. Okay, let's try 2 questions to make sure you know how to apply the formula, what we have learned. Page 220 to 227, number 18 and 20. Okay, what's the answer for this one? Energy stored in inductor is in electric field, magnetic field, form of heat, form of kinetic energy. What's the right answer?
Answer is A.
No. When you come to inductor, it's always changing flux. Changing flux is magnetic field, so it should be B. Right? So inductor involves magnetic field, so it must be stored in magnetic field.
Okay.
Okay, this one, just use the formula only. Can be quite simple. The multiple choice question. 0.6 Henry inductor carries a current of 0.25 ampere. How much energy is stored in the inductor? What is the answer?
Uh, 0.25 divide 0.6 times, divide 0.6.
Right, just half Li square. Half L is 0.6 Henry. I 0.25 ampere. So you get 18.8 or 19 millijoule. Okay, since they use 2 significant figure here, answer should be 2 significant figure also. Okay with that? Any comment or any question? Anything not clear?
No, I'm okay.
Okay, let's go to last section. Last subsection, mutual induction. Right? Mutual is
You
just like
finished
2.
17.4 already, actually.
Finish already, energy very short only, 17.4. Now it's 17.5, mutual induction. Mutual is 2%. Okay, 17.5, 2 hours. Explain the phenomenon of mutual induction and define the mutual inductance. Same as cell inductance, except this one involves 2 coils. Derive the expression for mutual induction between 2 coaxial solenoid of the same cross-sectional area. You can see the same formula. This is the length of the primary, number of turns of primary, number of turns secondary, area, area of secondary, and then there's the permeability of free space. Okay, let's try to understand what is happening. That's your coil A, that's your coil B. The switch is closed, so you got a constant current flowing there. Right? So we are just using Faraday's law. That is your Faraday's law. And then how to calculate your flux? Your flux is just BAN. And then remember, it's the current that create the field in the solenoid. Right? We are more interested in solenoid rather than coil. Right? But we use a loose term called it coil rather than call it solenoid. And our B is proportional to I. As I say, you can use a formula derived for use of cell inductance, but we won't do that. right? So when a steady current, right? Current is constant, flow in coil A, as a coil A, the magnetic field produced, right? Magnetic field is proportional to I produced by that coil is linked to the second coil, coil B. Right? It passes through coil B. Coil A, so coil A is called the primary coil. Coil B is called the secondary coil, right? Like your transformer. Right? As I1 is a current in the primary. It is constant. Study.
Teacher, can you repeat again? Teacher, everything, sorry.
When the steady current flows in coil A, right? It is when you close the switch, the current will initially rise and after that become constant. So if I is constant, your B is constant, and we call coil A primary coil, or coil B secondary, primary because that is where the current pass through. That's where the EMF is going to be induced, secondary. As the current I1, I1 is the current in the primary coil, is constant or steady. Remember, the current must change before you got dIdt here. No EMF is induced. Right? No voltage or no EMF is induced in the secondary if the current is constant. Right? Now we open the switch. Right? This coil, this primary coil, you open the switch, so the current will start to decrease. Right? It cannot simply disappear. It will start to decrease. When the current changes, remember, when the current changes, the flux, that B, from the primary is changing across the secondary. So it causes an induced EMF, right? Or induced current. So that induced EMF is going to produce a flux that is going to oppose this flux there, this direct flux. Right? So that's your induced flux or induced field opposing the primary field. Then Saw tell us that the induced current, right, that's your I2 in this coil, will flow to try to keep the field of A from decreasing. Right? That current is going to start to go to zero. So that field there is going to start to go to zero also. So that will be an induced EMF here or induced field here to try to keep this current going. That's the Lenz's law. Right? So if we close the switch again, right, that's why we have an induced EMF, right? In this case, right? Where the field is changing, that's the induced EMF here. That's why the meter shows. So when there is no more current, no more field, then we close again. Right? We can see that the induced EMF is in opposite direction. Same idea. Right? When the switch is closed, current starts to rise. It doesn't increase instantly. It starts to increase. The field produced, right? The field produced by this primary coil will pass through the secondary. So that means there will be a flux change in the secondary. Lenz's law tells us that an induced current in coil B, right? There's an induced current in this coil B, will produce a field to oppose. So there's a field passing through the coil. So the coil will produce an induced current to oppose the field. Right? Remember, that's your Lenz's law. You always want to oppose what you do. So if there's a changing current in the primary, there's a changing flux in secondary, it produces a induced current in the secondary.
So if both coil in producing current, then only will produce an induction flux lah.
So if the current is increasing, then there will be an induced current here or induced EMF here. That's why it shows it like in opposite direction, because this induced current is going to cause an oppose this increasing flux or increasing field. Okay with that?
Okay.
So that is why you call mutual. Right? Coil A, the current changing will affect coil B. Previously, is coil A, current changing affect coil A itself. But now we are not focusing on coil A itself. We are now changing current in A, will change the flux in B, so it will produce an induced current in B. That's what we call mutual inductance. So what is mutual inductance? It's the phenomenon. Phenomenon is what you see, in which EMF is induced in a conductor. Right? Usually a conductor is a coil, but we use a general term. Conductor can be a thin wire, it can be a coil, it can be a solenoid. Right? EMF is induced in a conductor when the current in the neighboring conductor changes. Right? That is the conductor. You change the current, that's your neighboring conductor, secondary coil, it produces an induced EMF. Right? So we can, that's your Faraday's law. Right? Remember that? We are just going to repeat again. Right? How to calculate your flux linking the secondary. And then remember the primary is produced by this current. So this current causing the change of field. Right? That field there. Changing current I in the primary will cause a changing field and thus flux linkage. Right? Flux linkage is just your B times A, AN, BAN. So it affects the secondary. Then EMF is produced. Right? There you have a change in flux linkage. You have an induced EMF. So we want to define mutual induction, M. Right? Mutual inductance. EMF E induced in the secondary is proportional to the changing current. Okay. That one we can do experimentally and derive this formula. Or we can derive it from Faraday's and Lenz's law. So from this one, we know there's a constant there. So we define mutual inductance by taking di dt down. Same, right? EMF induced, back EMF or EMF induced divided by di dt. Same with cell inductance. Cell inductance is only the coil. This one is mutual. Two of them, two coil involved. M is in Henry, same as I. M is a constant. We call it proportionality constant, and we give it a special name, mutual inductance. Right? And then remember, this is the EMF induced in the secondary. This is a changing current in the primary. Okay with that? There's a mutual inductance between the two coils. There's a EMF induced in the secondary. There's a changing current in the primary. Flux and mutual inductance. Right? Same. We just compare these two formula. Same. Cell inductance is your L, that's all. Derivation of mutual inductance, the formula for mutual inductance. Right? So if we have a current flowing in the primary, right? Current flow in the primary, this is alternating current supply. Magnetic field link the secondary, right? These lines are your B. Magnetic field strength or magnetic flux linkage. Right? It's going to pass through the secondary. So if this flux is changing, this field is changing, then you have a changing flux in the secondary. Okay, so your B for solenoid is mu naught and I. Right? This is all the primary. The primary is the one that produces the field. So if there's the length of the primary, there's a number per unit length. Then we can replace that number per unit length with the number in primary, number of turns in primary, divided by length of primary times your I. That's your I. Right? And mu naught is that mu naught. So flux in secondary.
Oh, this one.
Yeah. Okay with that?
No, the.
B.
Why were you looking inside that by this?
No, I didn't.
Yes, you did.
No, I didn't.
I used to. Should I ask him and see? You ask him to look inside there, not? Should I?
Hello, Che.
Okay. B is produced by primary, remember? That's how we calculate B produced by primary. And B will be changing if I is changing. Then in the secondary, right, there's a flux in the secondary is B, is B
Inama.
times area of secondary times number of turns of secondary. Right, put it in there. Right, that B is this one. And there's the area of secondary coil and S. Right, so rewriting it, right, compared to our that one that we have derived. Right, there's your I there. So we got your M. The others are M. You just take the I out. So you got M. Right, there's your mu naught and NTR. And then we got your A and S. Okay. Same with L. Same with your cell inductance. Cell inductance, that is for the two primary. There's only one coil only. That's all. Mutual inductance, that's a primary turns, that's a secondary turn. Mutual inductance, M, depends on cross-sectional area of secondary. Remember, not just memorize the formula. Remember what's A? A is a cross-sectional of secondary. Number of turns of primary and secondary is number of turns of primary, number of secondary. L is the length of the primary. Okay, try this question. The primary or transformer has 250 turns and a length of 8 cm, carries an alternating current of peak value 5 volt. The secondary has 1000 turns and our cross section area 40 cm per second. I just use a formula, that's all. Determine the secondary voltage. This one use your STPM work. The formula we'll go again after that if you have forgotten. Yep. Is it a step up transformer or step down transformer? Yep. Is it a step up transformer or step down transformer?
Transformer.
Cannot remember. Secondary, that's the number of turns in primary. Number of turns.
Oh yeah, I mean you determine which one has higher and lower, right? Yeah, based
secondary
on
higher.
turns.
So it's a step
I
up.
remember this in Sem 1.
You increase the voltage. Right? Primary is lower, secondary is higher, so the voltage is higher. Then we will go over that.
So step up plus step up.
I just try to just test you whether you can remember your STPM work. Right? For transformer, you have to remember this formula. Right? Voltage in the secondary, voltage in primary, secondary number of turns, number of turns in primary, and put in your value. Vs, Vp, take across there, and put in your value. Right? Primary, if you use peak, this will get peak. Peak means the highest value, the maximum value. You study in, under AC. Right? Vp is 5, Ns is 1000, that's your Ns. Np is 250, that's 250. And cancel that, it will be 4. 4 times 5 is 20 volt. And calculate your mutual inductance. Right? Just use your formula, that's all. Usually they ask you to derive it and then use a formula. Okay, we have to change in a while. Okay, that one get in from your physics constant data sheet. Area, remember to change the that area there, cross-sectional area of secondary, change it to meter square. NP 250, NS 1000. Then length of primary, change it to meter. So you got 15.7 millihenry. Okay.
Okay.
Okay, that's your transformer. If you look in your radio, you should be able to see that gadget there. That's your capacitor. Usually, this type is usually electrolytic capacitor. Transformer changes, that is transform and alternating PD from one value to another of greater is called step up, or smaller value step down, using the mutual induction principle. Okay, so that is a primary coil. Primary must be connected to an alternating supply here. And then you have a laminated soft core, soft iron so that it won't retain magnetism. It's become an electromagnet, temporary electromagnet. Laminated, because we don't, laminated means it's like sheets of paper lah. Right? The iron is in sheets joined together, insulated from each other, so that induced current cannot flow. Secondary coil, right? You don't need to know that deep. You just need to know what you have studied in STPM. Symbol, if there's a primary and secondary together, that's your air core. If it's an iron core, then you put a line straight through there. I think we will stop here. Give you 5 minutes break. Anything you want to ask?
Yeah, okay.
Rather than stop halfway.
No, teacher, but then instead 5 minutes, it become 10 minutes. I don't know why.
What do you mean?
Usually, then now he stop at 9:35, and then teacher give the link at 9:45, not 9:40.
Anyway, we record it down. As I said, we record it down. So they have no argument. 9:34 now, so we'll stop here. Okay. It's
Okay.
5 minutes
Thank you,
time.
teacher.
We see you.